Thank you for the introduction. Hi, everyone. I'm very excited to share with you how we used a decommissioned galaxy survey to perform the most comprehensive statistical analysis of stellar flares in the near and far ultraviolet. And I'll show you that 98% of flares in our sample display far UV luminosities above what's typically assumed. For anyone lucky enough to have seen the aurora borealis last month, here is the solar flare responsible for it, pictured in the extreme UV. And solar flares are these bursts of electromagnetic radiation caused by an extremely fast change in the topology of the magnetic field. It's called magnetic reconnection. And the term reconnection refers to the idea that oppositely directed field lines get too close to each other and break and cross-connect. That is unphysical. Really, there's a neutral point in the plasma where the field can undergo resistive diffusion at a much higher rate than the global diffusion. And this causes large amounts of magnetic energy to be converted into kinetic and thermal energy. And in the case of flares, causes particles to be accelerated downward into the chromosphere, heating chromospheric plasma. And um, and it's very visible, the amount of UV radiation that is created. This is saturating the detector. But flares on lower mass stars, particularly M dwarfs, can be 10,000 times as energetic as the most luminous flares on the sun. And while solar flares can contribute to the aurora or the occasional radio blackout, flares on lower mass stars can have a much greater impact on the planets which orbit them. In particular, flares could threaten or drive the creation of life. And quantifying the impact of flaring activity on habitability is an active area of research, but one way to do this is using a flare frequency diagram, which looks at the occurrence rates of flares of a given energy. And on this plot are two regions. The gray rectangular region is the ozone depletion region, a combination of flare rates and energies thought to be sufficient to deplete the ozone layer on an Earth-like atmosphere almost entirely and irreversibly. And then the green triangular region is the prebiotic chemistry or biogenesis region, which is a combination of rates and energies thought to provide enough near UV radiation to provide building blocks for RNA synthesis as sort of a minimum condition for habitability. And it's important to note that these regions overlap. So it's especially important to have accurate constraints on our rates and energies. I'll take you through placing a flare on this diagram. We start with a flare from tests. We have information in a single red filter. How do we go to a bolometric energy? Well, we extrapolate for the majority of flare emission. We assume some SED, typically a 9 to 10,000 Kelvin blackbody. We scale the SED to match the observed flux in the bandpass and integrate in space and time, and that gives us 1 point on this plot. And for the same star, we obtain more flares, ideally, so that we can reconstruct some sort of frequency distribution. And we repeat this process for many flares on many stars and see if any of them fall into these regions. And optical studies so far have typically found fewer than 10% of stars to fall in the ozone depletion region and even fewer in the prebiotic chemistry one. Note that if we were to increase the assumed 9,000 Kelvin blackbody, energy scales drastically with temperature, and we would have more stars falling into these zones. There has been great progress in the field in the last decade or so to study flares on a population level. Much of this has been done with optical missions like Kepler and TESS, and some of the largest flares have come from ground-based surveys like ASSASSIN. And these surveys have allowed us to get large samples of flares and place good constraints on the flare rates. But the energies often hinge on this assumption of a 9 to 10,000 Kelvin blackbody, which is largely untested. I've plotted it here alongside blackbody SEDs for 20 and 40,000 Kelvin as some of the few far UV flare spectra in existence have measured continuum temperatures up to 40,000 Kelvin. And as you can see, these optical instruments fall on the tail of blackbody emission, where it's hard to distinguish these hotter SEDs, and we're missing these wavelengths, which we think may be very important for habitability and which comprise possibly the majority of flare emission. So that brings me to the GALEX Space Telescope, which operated in the early 2000s and surveyed the entire sky save for the galactic plane. And GALEX detectors contained photon counters, which is actually really important because we can construct very high cadence light curves. And I'll show you an example in a moment. But GALEX observed simultaneously in the far and near UV, which allows us to probe these wavelengths that I've mentioned are so critical. So in an effort to obtain a volumetrically complete sample of flares, we looked to the Gaia catalog of nearby stars, which contains sources within 100 parsec. And we obtained simultaneous observations for nearly 200 flares on around 160 stars, the vast majority of which are fully convective, which is not too surprising since we expect these stars to be highly magnetically active. And I'll show you one of the most luminous flares in our sample. This is at a 10-second cadence. It's a very quick flare. And it's very far UV bright. As you can see, that's the blue light curve. And we can look at the relative amounts of emission in each filter to construct a color temperature. At flare peak, the far UV here is 2.5 times as bright as the near UV. And we can construct a one-to-one mapping between blackbody temperatures here on the x-axis and the far UV to near UV ratio on the y-axis. And note that this curve actually becomes asymptotic around 50,000 Kelvin when the blackbody gets so hot that even the far UV falls on the tail of the blackbody. And so increasing the temperature does not increase that ratio anymore. So in this case, we find this flare has a color temperature at peak of 30,000 Kelvin, which is extremely hot. Now, I'm going to share 3 results with you from our sample and 1 bonus result. The first is that, surprise, a 9,000 Kelvin blackbody is not sufficient to describe the levels of UV emission we observe. 98% of flares display far UV to near UV ratios with color temperatures above this value. So here we have a histogram of those ratios at peak brightness with bins by spectral type. And we have the typically assumed range of 9 to 10,000 Kelvin here in this black dashed line. And I do want to note there's a good amount of scatter here. Actually, a good portion of it is intrinsic scatter, not just attributable to measurement error. And finally, these kernel density estimates show some hint that we might move to higher far UV to near UV ratios with respect to spectral type. So this encouraged us to search for some correlations, which brings me to my second result. That there is a tentative weak correlation between the far UV to near UV ratio and G minus RP color, which is plotted here on the x-axis. And studies have shown that the transition to fully convective stars can be subtle, and so we may, in fact, expect a weaker correlation, which is exactly what we find. But we were also inspired to look at these ratios with respect to the flare UV energy. And again, we find a more tentative weak correlation between the far UV to near UV ratio and the flare energy. However, if we go from the lowest energy flares on this plot to the highest energy ones, we would expect the relative amounts of far UV radiation to double, which is not at all a trivial result. Now, I want to show a quick result from a work in progress, which is looking at the temporal morphologies of our flares and is allowing us to explore more of the time-dependent properties. And while I've shown you results so far for these ratios at peak, we can look at the relative amounts of emission through the flare duration. And we do just that. Here is a stacked histogram of all of our flares normalized in space and time. And we find that the far UV to near UV ratio evolves over the course of the flare, and it increases in the impulsive phase going up to flare peak. In addition, we find that over the entire duration, the ratios typically fall a good amount above the 9 to 10,000 Kelvin range, which is typically assumed. Now, it is possible that the flares in this sample are pretty universally hotter than 9 to 10,000 Kelvin, or there could be significant contributions from line emission in far UV. And ideally, we would obtain lots of spectra for stars while flaring to be able to distinguish those contributions. But as I mentioned, there are very few. One of the first of which is from a super flare on AD Leo from the 1980s. And this spectrum showed increased line emission, but was still found to be dominated by a 9,000 Kelvin blackbody continuum. And this spectrum has been used in photochemical models, and I think is a big reason that the 9,000 Kelvin assumption has become somewhat of a standard. But this and the other far UV flare spectra that I found in the literature have all found that the blackbody continuum remains the dominant energy source. And then, but this is not always the case on the sun. Here's an example of a line-dominated flare on the sun. But there are some big differences between the spectra in terms of the flare energies, the type of star that is flaring, and the spectral resolution. And so we really can't say at this point how much of the emission is coming from lines versus a hot black body. Now, there is a bit more work we'll be able to do with this sample. We have heard a lot in this session about how to constrain the stellar magnetic fields, and the G-RP color that we used is really just a preliminary diagnostic. We'd also like to constrain stellar ages through kinematics, although that's hard for M-dwarfs. And returning to this flare frequency distribution, the optical studies used to place stars on this plot, as well as the photochemical models used to create those regions, all rely on assumptions about flare emission that we've shown may not be reasonable. There is some hope with, well, the landscape for far UV spectra is extremely limited now and in the future with Hubble, however risky and expensive, and with UVEX coming in the 2030s. And there are some really exciting missions which will provide UV photometry. MANTIS will observe alongside JWST. EUVST is a solar telescope. Ultrasat will provide near UV photometry. And I also encourage people to look at all of the posters the next couple days on some really awesome multi-wavelength flare studies, which I think will be helpful to study this emission as well. But with that, I'll leave up my summary slide. Thank you for your time. Oh, yes, I forgot to mention we don't have rotation periods for these stars. The question was, have we compared our results with X-ray data and have we looked at the rotation periods? Did I miss anything? Okay. So we don't have rotation periods for these stars. I forgot to mention it would be great to have those. And we haven't looked at X-ray data yet, but I think a lot of times you see a similar trend in having super, super hot temperatures in the X-ray. And like I mentioned, I think there are some posters the next couple days with X-ray flare data. So I'll look out for those.
That's it for this session. Thank you, Vera. Let's thank Vera and all of them.
Whoa. Oh, sorry, Jeff.